Okay, thank you very much. First of all, I would like to thank the organizers for the kind invitation. It's a great pleasure to be here at this nice conference. My talk is on causal variational principles, and in order to put this into context, I thought that I best begin with a schematic overview. So here on the left upper corner, we have globally hyperbolic Lorentzian geometry. This is, of course, what we are all familiar with. And now we can embed this setting to the setting of causal fermion systems. Causal fermion systems, so this is my main area of research, and this is mainly concerned with the quantum world. So one has like quantum spacetimes, a quantum wave function, quantum fields, a quantum geometry, but there's also a classical limit in which one recovers classical fields, also the Einstein-Hilbert action, classical GR, and it can all be done in a non-smooth setting. So this is why it should be of interest to all of us. But I thought that introducing all of this is a bit too much. We really want to do math, and I don't want to just show you the basic definitions and explain them. And this is why I decided to restrict attention to time-independent setting in this systems in this talk. Then on the left side, we have static spacetimes or ultrastatic spacetimes, and correspondingly on the right, we have static causal fermion systems. And the setting here can be embedded or generalized to what we call causal variational principles. And simply, we don't use all the structures, but only a subset of them. And this is quite a nice and convenient setting to work in, as we will see. So what I will do in the talk is I will begin with causal variational principles. And later, I will explain you the connection to causal fermion systems. In particular, I want to explain you what this red arrow is. So how do you get from static spacetimes to the setting of causal variational principles? But as I said, let's begin here with causal variational principles. What is the general setup here? So we start with a manifold G whose dimension is much larger than 4. In fact, smoothness is not at all important here. So if you like, you can also replace G by a locally compact topological space. But I thought that for the audience here, it's better to work with a manifold because we are more familiar with that. Okay, next we introduce a Lagrangian, which is a mapping from G cross G to the positive real numbers, which has the following properties. First of all, it is continuous. In fact, lower semi-continuous is sufficient, but this doesn't matter for the purpose of the talk. So let's suppose it's a continuous function. It's symmetric, and moreover, it's strictly positive on the diagonal. So L of XX is positive, strictly positive for all x in G. And next, we consider a regular Borel measure on G. And this makes it possible to write down the action. So the action looks as follows. So we take the Lagrangian and integrate both arguments with respect to the measure mu. But the setting looks a little bit like, at first sight, it looks a bit like octal transport, what we had in earlier talks. You could say, well, this is similar to the cost function, but there's a major difference. I mean, the mu is not a measure on the product, so it's not a measure on G cross G, but it's really a measure on G itself, and this is why we get a double integral here. Okay, so this is the action, and now the causal variational principle is to minimize this action under variations of the measure mu, keeping the total volume fixed. Okay, now suppose you consider a measure of finite total volume, say probability measures, then it's clear what it means to keep the total volume fixed. However, we are mainly concerned with the case where the total volume is infinite, and therefore the question is how to keep the total volume fixed if the total volume is infinite. And the way this works is as follows. So this is a definition. What is a minimizer under variations of finite volume? And we say, well, measure mu is a minimizer in this sense. If for any measure mu hat, which has the property that the total variation of mu minus mu hat is finite, in this case, we can speak of the total volume of the difference, and this should also be 0. If we consider such measures, then the difference of the actions should always be non-negative. So in simple terms, what we do here, so we keep the measure mu fixed, except on a set of finite volume, and on this set, we replace it, the measure by any other measure, which has the same volume. Okay, now you might wonder, well, what is here the difference of the actions? One has to be careful because the action itself could be plus infinity. So then, of course, plus infinity minus infinity doesn't really make sense. But the way to do this is as follows. Namely, we write this difference like this. So we replace mu hat by mu plus mu hat minus mu. And the action is kind of bilinear in the measure. So we can multiply all this out. And then the infinite term drops out. And what remains is this combination. And you see there's always like this red difference coming up. So this is why everything is now well-defined and finite. And this is what we take as the definition of the difference of the measures. And doing it like that is really like a sensible concept. In fact, minimizers exist under general assumptions. This is something I proved a few years ago with Christoph Langer. More precisely, the setting is so-called sigma locally compact setting. So we assume that G is the countable union of compact sets. Okay, but let's not worry about existence of minimizers. In what follows, let's just assume that a minimizer exists. How does this typically look like? I mean, just to give you an impression, suppose the whole blackboard here is the manifold G. So as I said, you should think of it as being very high dimensional. And then we have a measure on G. Its support is what we denote by N. So this is then what is space or space-time, depending on which setting you are in. And the typical situation is that this support is very low dimensional. Or say more precisely, it's containing a low dimensional subset of the manifold G. And the support here doesn't need to be smooth, as I indicated here by this cast. It could even be a discrete measure. There could be individual points here, could be counting measure, whatever. Okay, so this is how this looks like. Good, so now we have this action principle. We minimize the action. What does this actually mean? And this is like an important question. And well, in fact, most of the talk will be concerned with understanding what minimality means. And one way of understanding is by deriving the corresponding Euler-Lagrange equations. Let me explain how this goes. So let's assume that L is a minimizing measure. Again, N is the support of this measure. Now we choose a subset of N of finite volume. And now we consider, now we choose also a point in G, which does not need to be on the support of the measure. And now given a parameter in between 0 and 1, we consider the following variation. So chi here is always a characteristic function. So here we have, so this means that outside the set omega, the measure mu is unchanged. Inside the set omega, we multiply it by the scaling factor, 1 minus tau. And then here we have the Dirac measure at the point x, and this factor here makes sure that the total volume is preserved. So therefore, this is a measure which satisfies the volume constraint, and therefore we can use it for testing. So we know that this difference of the actions is always non-negative for all positive taus. Of course, tau cannot be negative, otherwise it's no longer a positive measure. Okay, if this is positive for all tau, and of course it is 0 if tau is equal to 0, then also its first derivative is non-negative. In other words, we linearize in tau. And now we have here an inequality, and you can in fact differentiate the intervals and work all this out. And what this gives is the following result. So we introduce now a function little l, which is obtained from the Lagrangian by integrating over one of the arguments. So it's still a function of the other argument. And then we subtract a constant. And then the statement is that if you have a minimizer, then for a suitable choice of this constant, this function L is minimal on the support and vanishes on the support. So it's constant on the support, and it's in fact minimal there. I mean, this is shown here in this one-dimensional example. Suppose this is G. The support is this red subset, and on the support, this function L is constant, and this is in fact the minimizer. Excuse me? For sure, M should be N. Usually in the space-time setting are denoted by M, and here I just forgot to make this replacement. Well, here just think of it as space, because I'm only considering the time-independent setting. If it's M, then it's in fact space-time. I will come to this later. Okay, so this is how this looks like. And well, the question is, can one do better? And in fact, one can do better by exploiting kind of this minimality condition, not just by linearizing, but in a more nonlinear setting. This is what we denote by nonlinear positive functional, and this is in fact quite recent. I mean, this is joint work with one of my long-term collaborators, Nikki Cameron, from McGill University in Montreal. So we started kind of last summer with this. And in fact, there's no preprint yet on the archive, so we're just in the process of writing it up. So you might think, well, it might be a bit premature to talk about this. On the other hand, in this way, I can get early feedback by all of you. And the idea, in fact, is quite simple. So now let's assume we have a minimizer. You can think of it as the vacuum. And now we have another measure, mu tilde, which we assume to be critical. So critical means that this function little l is 0 on the support. And its support is n tilde. So always tilde refers to the interacting or curved space-time or space, and no tilde is the vacuum. Okay, and now similar to before, now we choose a subset omega, and we choose a subset omega of n, a subset omega tilde of n tilde, and we assume that they have the same volume. And now we take out this part here and replace it by the part over here. So this is the formula. So outside omega, we leave the measure unchanged. While in the inside omega, there is nothing anymore. Instead, we take the measure mu tilde on omega tilde. Okay, so this is again the measure, and this satisfies the volume constraint simply because we assume that these two sets have the same volume. And therefore, we again know that the difference of actions is non-negative. And now one can write all this out. And then you get this. This is what you get. So you get 3 double integrals. I should say always one integral is over omega tilde, so this bounded region. And the other integral is over the complement. And here you have twice the measure mu tilde. Here you have twice the measure mu. And here you have a mixture. So one integration over mu tilde and the other over mu. Good. Now the question is, what does this mean? And in fact, it has a simple kind of geometric interpretation. Let me explain this. Well, first of all, the volume of omega denoted by V, and similarly with tildes, tilde always is the interacting spacetime. So we have volume, of course. And now let's consider this double integral here. So as I said, so one integral is inside, the other integral is outside. So here's like a picture. So x is inside, y is outside. And now in typical examples, well, I haven't specified the Lagrangian here yet, but I mean, if you consider concrete examples, then the Lagrangian typically decays if the points x and y are far apart. And the corresponding length scale is, say, the Compton length, if you want to make this specific. So as a consequence, you only get a contribution if these 2 points here are sufficiently close together. And since one is inside, one is outside, this means that both points need to be near the boundary. And this is what we call a surface layer integral. And in this surface layer integral here, so we can say, well, this is what this is how we can define the area of this region. Maybe just as a remark, I mean, these surface layer integrals, they come up very often in this whole context, also the time-dependent setting. For example, this thickened Cauchy surface, which we talked about this morning, can be realized using this concept of a surface layer integral. So a Cauchy surface here corresponds then to a Cauchy surface layer. Okay, so now we have volume and area. Now we have this integral where one integration is with respect to mu tilde and the other with respect to mu. And this is what we call a nonlinear surface layer integral, which intuitively speaking makes it possible to compare the two different spaces near the boundary. So I mean, here's a picture, so we have again n and tilde. So x has to be close to the boundary on n tilde, and y is close to the boundary on n. And this whole combination is positive. But in fact, so this was only the simplest version. I mean, there are other variations of the same idea. So this is what we just derived. So this nonlinear surface layer integral minus the area of omega tilde minus the area of omega is bigger or equal to 0. And this was under the volume constraint and assuming that mu tilde is critical. If we drop this volume constraint, then you again get a positive quantity, but you have an extra term here. And you can think of this S here as the action per volume, if you like. If you remove the criticality, then you get an additional term, which looks like this. Okay, so these are different variations of these positive functionals. But the next question is, well, what can you do with this? What is the application of this? And one application is to the total mass. Now let me explain how this goes. Again, we have two spaces, n and n tilde, corresponding measures mu and mu tilde. And now we exhaust them by sets omega n and omega n tilde of finite volume. And we assume that the volumes are always the same. For every n, these two sets have the same volume. And now we take this positive functional, which we just had before, and take the limit n going to infinity. And it turns out that if you take this limit, then one gets back the total mass, which are introduced together with Andreas Platzer a few years ago. Let me explain a little bit the connection here. I mean, back then, so this was 4 or 5 years ago, we were not interested in positive functionals, but in conserved quantities. So we were asking the question, can one introduce a quantity which does not depend on the choice of the exhaustion here? And then we came up with surface layer integrals with a specific structure. And this is how we could define the total mass. And we verified that if you take, for example, Schwarzschild spacetime, then you really get back the ADM mass, which was introduced in yesterday's talk. Okay, so this is the total mass here. And well, and here's a completely different approach. We consider positive functionals. And it turns out that in the limit, we get the same functional which was already conserved. So in this way, things fit together. So we have both conservation and positivity. And this is why we get a positive mass theorem here right away. Maybe I should say, I mean, here the title was also a positive mass theorem. But what we did here was a bit more classical. So we assumed that we introduced a notion which corresponds to local energy density. So we assumed that this was positive. And as a consequence, also the total mass is positive. And the proof was kind of inspired by Witten's proof. In any case, I don't want to enter the details here. So here, this is kind of the same, in the same spirit as the usual positive mass theorem. Here it is in fact quite different because we get positivity without any local energy condition. So somehow the variation principle also arranges by itself that the local energy condition is fulfilled. And the total mass you get is always non-negative. Okay, now the question is, well, what does it mean here locally? Can one make this precise? But maybe before explaining this, I want to show another application of this, namely in this work with Andreas Platzer and also what I showed you so far, we have to satisfy this volume constraint. And this is a bit artificial because if you think of the ADM mass, this is defined only via the data on big surfaces or on the boundary of big sets, but the interior volume never comes into play. Okay, and now it turns out that using this new functional, we can in fact get rid of this extra condition. And what we do is, well, now we have to identify the spaces near infinity in the kind of optimal way. This is what we call they must be asymptotically aligned. And if this is done, then we can modify the space in the interior as shown here by the support of mu tilde. And then by comparing mu tilde with mu, we get the positive mass theorem without any volume constraints. Okay, but now let's move on to this kind of what are localized versions of this statement. Let us first of all define a quasi-local mass, which is in fact quite simple in this setting. We just take a subset of n tilde, And now we consider this positive quantity, which I defined earlier. And then we take the infimum over all sets omega. And there's one more thing here. I mean, here I allow for an isometry. So I mean, I say, well, of course, there's no Riemannian metric here. So what I mean by isometry here is simply that the Lagrangian is unchanged if both arguments are transformed. So I is a mapping from G to itself with the property that the Lagrangian is preserved in this sense. And then I allow that one of the sets here, doesn't really matter, is isometrically transformed, and then I also take the infimum over all the isometries. The way to think of it is as follows. So suppose this is here our vacuum. We consider this set omega tilde. With this isometry, we can kind of move this around and try to make this fit as good as possible. And then we consider our positive quantity. And this is how we define the quasi-local mass of this region. And when you now look more closely to the result, how this mass here looks like, then it's in fact quite similar to the Brown-York mass. I mean, just as a kind of recap, now what is the Brown-York mass? In this case, it works as follows. You take like a subset of your curved space, and now you embed this into Euclidean R3 in such a way that the boundary is embedded isometrically. And you have to assume some convexity, maybe that's not so important here. And then one integrates the mean curvature over omega with respect to omega tilde with respect to omega and takes the difference. So this is the Brown-York mass. I mean, this was then later generalized, extended by Shitem, Liu, Wang Yao, and many others. And now it turns out, now if you look at the formula for the area, maybe I should quickly go back. Here, well, I said this is the area. But in fact, it is only approximately the area. I mean, if you kind of expand this in this parameter d here, then the leading term is the area, but the next term is then in fact the mean curvature. And then if you then consider this combination here, then the leading term in fact just drops out if you embed this properly. And then what remains is the next term. And this should then be, just give us the Brown-York mass. I should say that we haven't worked out the details yet. I mean, I'm just conveying you the basic idea. Now, what about scalar curvature? Now, we want to localize it even more. And the idea is if you take a sufficiently small spatial region, so then the metric is nearly flat, say, or like, so then if using this isometry, you can always make a perfect match, but not quite. And this deviation, this is something which can then be described or should be possible to describe as a linear perturbation. So we choose here a vector field which points from the unperturbed spatial point to the other point. And also the weight of the measure could change. So this is why what we get here is what we call jets. So this is a combination of a scalar function, which changes the weight, and of a directional derivative, and the vector field tells us how the support changes. Okay, and now if you want linearizes, then this positive quantity can be written like this. It is like the integral over space over what we call the Laplacian, or this is the linearized field operator, as it's called, and this comes also up in many other works in this context. So this is really kind of a basic operator here, which really takes the role of the wave operator or the Maxwell operator or whatever. So this is how this looks like. So it involves like kind of linearized. So this is why linearized, as you have here, you have one needs to differentiate. I should say maybe also from here on, we should better assume that space-time, that n here is a, say, three-dimensional manifold. Okay, in fact, not necessarily, but at least, I mean, it's a bit easier to do it that way. Okay, so in other words, we can introduce here a linear operator, which is in fact non-local, because this non-local kernel here comes up. And then the mass can be written as minus the integral of this Laplacian V. And therefore, it is kind of natural to say, well, I simply define scalar curvature as minus this Laplacian, and then I get this usual Newtonian formula. The mass is just the integral over the energy density. Of course, this holds only linearly, and this whole nonlinear picture, this is like what I showed you earlier. Okay, and this scalar curvature can really be positive or negative. In fact, if you have a minimizing measure, then if you take a perturbation which preserves the Euler-Lagrange equations, then it has to be positive, as I showed you earlier, because I mean the variation principle by itself arranges this positive scalar curvature property. Okay, so I mean this is what I wanted to say here. I mean, I think then the next part is how do you get from spin geometry to causal variational principle? So this red arrow. Unless you have questions, I mean, I could just move on there. Let's see. Okay, good. Good. Then let's start with the Lorentzian spacetime, say 4-dimensional, globally hyperbolic. And if you want to keep things simple, you assume it's ultrastatic, and then we have here Riemannian metric. So this is the Riemannian metric which we all know and love. And in this setting, everything is spin, so we can introduce the spinor bundle, and we can formulate the Dirac equation. And somehow the whole approach is kind of based on the Dirac equation and Dirac spinors. In this ultrastatic setting, we can write the Dirac equation in the Hamiltonian form. So we have here like a Hamiltonian, which which acts on sections on a Cauchy surface, and which is a self-adjoint operator. And we can also, of course, solve the Cauchy problem just exponentiating. Good. And now, in order to get into the setting of causal fermion systems, one chooses a subspace of the whole solution space. For example, you can take the negative spectral subspace, in other words, all the negative energy solutions. But in fact, it doesn't really matter so much which subspace you choose, but it has to be sufficiently large. So let's just take all the negative energy solutions. Next, we need to introduce a regularization operator, which kind of smears things on a small scale. And in this example here, we can just take the operator e to the epsilon h, where since you only consider the negative spectrum, this is something which really decays. So it gives us like a kind of smooth cutoff for high energies. Good, and now we introduce an operator, so-called local correlation operator, which is defined as follows. I mean, if we take this, say, if we fix the space-time point Tx, and then we can evaluate this kind of regularized wave function at this space-time point. And then we can do the same with psi and phi. So in this way, we get like a sesquilinear form on our Hilbert space at this given space-time point. And now we represent this sesquilinear form using the Fréchéry's theorem by an operator on the Hilbert space. So we use this capital F here as a kind of a signature operator to represent this spin inner product, which is used here in terms of the scalar product. This construction gives us a self-adjoint operator of rank at most 4, a finite rank operator, which has at most 2 positive and at most 2 negative eigenvalues. And the set of all these operators, this is what we denote by curly F. And this plays the role of kind of the ambient space in which everything takes place. And this is also why it is very high dimensional. Good, so this is what curly F is, and now we have to construct the measure. And this works, yes? Excuse me? I see, the rank 4 condition comes from because here, I mean, here we have the spinors at a given space-time point, so it has just 4 complex components. And then you take the product at one point. So therefore, here everything takes place in a 4-dimensional vector space. I mean, you can also do it in a little bit more sophisticated way, if you like. I mean, you can say, I introduce an evaluation operator, which psi maps to psi of t comma x. So from our Hilbert space to the spinor space at the point x. And then in fact, this f of tx can then be written as minus etx star times etx. And then you see here, I mean, since this maps to a four-dimensional space, it can have rank at most 4. And then if you take this E star E combination, the rank stays at most. Okay, good. So this is like kind of our base space. And now in order to construct the measure, what we do is the following. I mean, now we have a mapping which to every space-time point associates an operator here to the right. And now we simply take the push-forward measure, defined like this. Now we have a measure on the set of linear operators. And once we are here, we forget about the left side and we work only on the right side. And the support of this measure, this gives us back the image of F, also in other words, gives us back our space-time. So this is the picture. And this leads us to this general definition of causal fermion system. So you have a Hilbert space. You're given a parameter and a spin dimension, which in this case is always 2. And now we consider the set of linear operators, which are self-adjoint, have finite rank, have at most n positive, at most n negative eigenvalues. And finally, we consider a measure on curly F. And this is how you can think of it. It's similar to what I showed you before in the time-independent setting. Okay, now how do you get to the time-independent setting? Well, I started from an ultrastatic space-time. So there is this unitary time evolution. And it also gives a time evolution for these local correlation operators. And our measure is also time invariant in this sense if we start from a static system. So therefore, our measure can be written as TD mu, and now mu, this is in fact the measure which I started from at the very beginning. And G can be defined as F modulo R. So in other words, in simple terms, you simply mod out the action of the translation, of the time translation group, and this gives you G. So G is again like a set of operators, modulo, or like equivalence classes of operators on the Hilbert spaces. And then there's an explicit Lagrangian. How is this Lagrangian defined? Let me see. Okay, I think I still have time for doing that. So this is this causal action principle, which works as follows. I mean, suppose now we take 2 points in curly F. So these are operators, and we can multiply them together. If we do that, then we again get an operator which has rank at most 4, but it's in general no longer self-adjoint, because if you take the adjoint and the order of multiplication flips, and since the operators do not need to commute, we get something different. So this is a non-symmetric operator. As a consequence, it has in general complex eigenvalues, but since we have rank at most 4, only 4 of them can be non-trivial, so all the others are 0 anyway, so we only consider 4 complex numbers here, the 4 complex eigenvalues counting multiplicities. And then we write down the Lagrangian in this way. We take absolute values of the eigenvalues, subtract them, square it, and sum over all the eigenvalues. So this is the causal Lagrangian. Now in the static setting, one has to integrate over time. In order not to get infinity, I mean, one just integrates once over time. And this is then the static Lagrangian. And I should say the causal action principle comes with constraints. Well, first of all, the volume constraint, this is the one we keep. But there's also the trace constraint and the boundedness constraint. And they are built in here by fixing the trace and by adding a Lagrange multiplier for the boundedness constraint, just in case you already know the setting. Otherwise, this is not important. Okay, so this is like how it works. And let me try to summarize this. So this is my last slide schematically again. So we started here with an ultrastatic space-time. And here, of course, the Riemannian metric comes up. And then we constructed a family of spinorial wave functions. And well, and what we do in this step, I mean, well, I mean, generally speaking, I mean, like here we are concerned with like non-smooth geometry, so whatever we all agree that the smooth metric is not sufficient to work with. So, and then one can say, well, let's relax the regularity. It should be only Lipschitz or whatever. Yes, but ultimately, one should give up the metric. And then the question is, well, if you no longer want to have a metric, then what should we have instead? In fact, we already saw this approach with Lorentzian length spaces, for example. Maybe we no longer have a metric, but we can still speak of the distance of space-time points measured by considering shortest curves between them. Well, here the philosophy is a bit similar. So we want to give up the metric, and the question then, what remains? And what I want to propose is that what remains is really this family of spinorial wave functions. I mean, they no longer satisfy the Dirac equation because you can't write down the Dirac equation anymore if you have no metric. But still, you can speak of a family of spinorial wave functions. And from the metric, only the measure should remain. So in other words, this determinant of GD3x, I mean, the volume measure, this is something we want to keep. And all the other structures we drop. Okay, and then the information contained in all of this is encoded in the measure mu on G. And this is more a matter of mathematical convenience. In this way, you can get rid of local gauge freedoms and things like that. So, but well, as you prefer. I mean, either you think of this measure on linear operators, or if you prefer, you can also think of this family of spinorial wave functions in space. And there's also a measure. Good, and then we have this Lagrangian, which is defined via the eigenvalues of operator products, and this gives us this causal Lagrangian. And okay, I think this brings me to the end of the talk. I hope I have convinced you that really looking at such variation principles really seems to capture a lot of interesting physics even. I mean, you kind of get an understanding why is the mass positive, you get a simple proof of a positive mass theorem and of whatever local curvature quantities. Of course, there would be a lot more to say if I moved on to the space-time setting, but I think that's enough for my talk. So thank you very much.